let's just talk a little bit about lab number 7. It's a flame test. Now, there are several ways to do flame tests. This is a classic. You take a Bunsen burner, you have a glass rod with a piece of platinum wire coming out. You dip this in a metal salt, stick it in the flame, and you get a color. And, well, that's not really exciting, I suppose, but it's fun still. We're going to do flame tests, but we're not going to do it quite this way for a couple reasons. First of all, there's a more exciting way to do it. And second of all, this is supposed to be a platinum wire. And every time they buy glass rods with platinum wires, somebody cuts off all the platinum pieces and takes them home. So we have to use nitro, which doesn't work very well. So instead of using the wire dip method, we're going to do the blowtorch method. Much more fun, much more exciting. What you do is you have a flame here, a Bunsen burner. This is a little compressed thing with metal salt in it and alcohol. And you, in the hood, very carefully, not pointing at anybody, you push the button and you get whoosh. So it's a lot of fun. And you know the color. Now the color, this is strontium actually. Color is not perfect, but this is strontium. The color that your eye perceives is actually an average. Something called an emission line spectrum. The color can be resolved using something called a spectroscope. And this is for a fluorescent light. And we're going to hopefully do this if they can find us spectroscopes. If you look at the fluorescent lights, they're kind of whitish, right? Well, that's an average your eye is doing. This is the light broken down by wavelength. And you see we have blue bands, green, red, whatever. And your eye averages all this and makes white. So we'll kind of do this too. Now, what's really happening here, you're taking this metal salt. So this is an atom, and the little rings here represent quantum levels, okay? When you take these electrons, the core electrons that we don't care about, and you stick them in something like a flame, they get very excited, and they absorb energy, and they move from whatever quantum level they're in to somewhere else. Now, they're sitting up here, you know, the view is great, it's a nice place to be, but they know they shouldn't be there. So what they're going to do is drop back down to where they used to live, and when they do that, they're going to emit the energy that they absorbed. Okay? Now they're going to emit it as light, but it's a single wavelength because remember this is quantized. It's going in steps. So when this comes back down, we get one wavelength. When this one comes down, we get a different wavelength. And if we look through the spectroscope, we can resolve these. Now since every element has a different electron configuration, every element has a different emission line spectrum. That's how you can take a star that's 100 million light years away and know exactly which elements are in there. It's really kind of neat. To resolve it like this, we use, like I said, a spectroscope. It's really fun to watch people try to use them because the little opening here goes to the light source, but you have to look in at this angle. And the coordination is a lot for some people. Nonetheless, you look through here, Again, we're going to look at fluorescent lights, and you should be able to pick out the emission lines. Now, the blowtorch method is most certainly fun, but the absolute best one is something that I did once, and they won't let me do it again, won't let me do it here. But what you do is you get the lab totally dark. You take all of your salts, put them in little watch glasses, douse them with alcohol, then you light it at one end, and it goes poof. Looks kind of like this.
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with the barium ions burning a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally potassium with the purple or lilac shade.
Now, like I said, this is a really fun thing to do, but you do have this big desk that's all on fire, and like I said, they frowned upon it, but it was fun. If you think about it, this is where fireworks come from. These are all different metal salts, and depending upon what color you want, you mix the salts in with the gunpowder, and you get a color. So something like this. We have the purple, lilac, we have copper, here we have sodium. This is probably selenium. Strontium here, whatever. It's kind of neat, actually. Any questions? All right, speaking of neat, we're going to talk about chemical reactions today. This is the thermite reaction, where we take aluminum, iron 3 oxide, make iron metal, and aluminum oxide. It's a very explosive sort of reaction. Again, it's great fun. Can't do it, but we have a couple nice videos. So let's go back and start all the way in chapter 1-ish. We were talking about compounds, chemical reactions, aluminum and bromine to make aluminum bromide. We have reactants, we have products. We know that it's a chemical change because the chemistry of the original reactants has totally changed when we make the new compound. Totally different physical and chemical properties. Now, we link these two together using the reaction arrow. We said the reaction arrow has the same properties as an equal sign. That means the same number and types of atoms on both sides of the equation. If we look at the coefficients we've stuck in here, this is 2 aluminum, 3 bromine, 2 aluminum bromide. The little letters down here indicate the state. Now they're optional, but S is for solid, liquid, gas. AQ is aqueous solution, so that's in water. Now we can also express this in terms of moles. When we use moles to describe a reaction, that's called the stoichiometry of the reaction. Now, stoichiometry is a really neat sounding word. It's a simple concept, but it sounds neat. You can go home and tell people we did stoichiometry today, and they'll be so impressed. Really, all stoichiometry refers to is expressing the coefficients here in terms of moles. 2 moles of bromine, 3 moles, 2 moles of aluminum, 3 moles of bromine, and 2 moles of aluminum bromide. Now, we know we can express moles in terms of mass as well. So this also comes out to be something like this. 54 grams of aluminum, about 480 grams of bromine, to give us 533 grams of product. And if you're able to do math quickly in your head, you'll note that this plus this gives us the mass of the product. So again, the equal sign refers to numbers and types of atoms and mass. Now, where do these coefficients come from? Well, this is the process of balancing an equation. Now, there are lots of ways to balance equations. We're going to do it, quote, by inspection. A couple of rules, but basically by inspection. There are matrices you can write, there's computer programs, etc., but inspection works. If we take hydrogen peroxide, this will decompose spontaneously to form oxygen gas and water. But if we look at this equation, it's not balanced, is it? We have 2 hydrogens here, 2 hydrogens there, that's good. But we have 2 oxygens and 3 on this side. That's not good. So this is a case where we have an even number of atoms of one type on this side and an odd type on the other side. This is an even-odd thing. The way I go about balancing is I look for even and odd discrepancies, and then I try to make everything even or everything odd. Okay? Now, to make this even, oxygen, the simplest way would be to put a coefficient of 2 in front of the water. That gives us 2 oxygens, and that gives us, well, let's see, 1, 2, 3, 4 oxygens, and 2 on this side, but it's an even number. Okay. But when we've done this, we realize that we have made 4 hydrogens as well. We only have 2 on this side, so we can fix that by putting the 2 in front of that. So let's do our bookkeeping. On this side, we have 4 hydrogens. 4 hydrogens. We have 4 oxygens. 1, 2, 3, 4 oxygens. And by George, we're balanced. That's simple. Right? Right. Well, it does take a little bit of practice. We'll get lots of practice. This is an exam question that I gave on the second hour exam once. It was a combination of nomenclature and balancing equations. So, look at this and see if you can start off by writing the equation. Potassium chlorate decomposes to give oxygen gas and potassium chloride. All right, chlorate, we remember, is ClO3, right? -1. Potassium is group 1, so it's +1. So this is simply KClO3. Oxygen gas is a product. Remember, oxygen is one of our diatomic elements. So it's going to be O2. Potassium chloride, group 7, group 1, +1, -1, simply KCl. Link it with our arrow, and this is our basic equation. Now, it's not balanced. 3 oxygens, 2 oxygens. So step 1, let's make it even on both sides, and we'll double the KClO3. Simply stick a 2 in. All right, that has given us 6 oxygens here. We only have 2 on this side, but they're even, so we can multiply this and give us 3. Finally, when we doubled the potassium chlorate, we had 2 KCl's, only 1 here. Let's double that. And by George, we have balanced our equation. It's kind of fun, actually. It is, like a crossword puzzle or something. Kind of fun. This is also a very neat reaction. It's one that they will let us do in lab, but we don't. If you ever need a little bit of pure oxygen for something, what you do is take potassium chlorate in a test tube, heat it up, and it evolves oxygen gas. That's a good thing. And that brings us to the gummy bear reaction. Now, this is the gummy bear. We have a tube full of potassium chlorate that we've heated up. A gummy bear is essentially pure sugar. It's also, the whole medium is very hot because we've melted our potassium chlorate. The oxygen that's formed reacts instantly with the sugar, which is the gummy bear. These two react, we get CO2 and water. So let's look at the video. Take our poor little gummy bear. Here's our tube. Drop it in. It's a fun thing to do, but don't show it to small children, okay? And when we're all done, there is no more gummy bear. There's simply a little bit of leftover potassium chlorate, water, and potassium chloride. Any questions? Well, let's see if we can do this. Let's balance some equations. Now I'm going to take a chance and try to do this in real time. I'm not looking at the answers, right? Our first one, we have 2 hydrogens, we have 3 hydrogens. Let's double this. Oops. Oops. Try again. Let's double this. That gives us 6 hydrogens and 2, so we need a 3 over here. We have 2 nitrogens, we have 2 nitrogens, 6 hydrogens. I think it's right. Got it. I love it when I get it right. Zinc plus HCl gives zinc chloride and hydrogen gas. We have 1 hydrogen, we have 2. Let's double the HCl. Now we have 1 zinc, we have 1 zinc. 2 hydrogens, 2 chlorines. I think that's all we had to do. Now look at this last one for a minute before I do it. I would look at this and say 3 oxygens, 2 oxygens. First thing I would do is double the iron 3 oxide. All right. When I do that, that gives me 4 irons, right? So I need a 4 over here. It also gives me 6 oxygens. I only have 2 there, so I need a 3 here. And we have 12 chlorines, only 2 here. They come as pairs, so we need 6, I think, right?
Yeah.
Yes. Now, let me hush for a minute, and you guys can do this one. In our first one here, we have 2 hydrogens there. We have 1, 2, 3 on this side. Let's fix that by putting a 2 in here. All right, now that gave us 2 sodiums on this side. Let's put a 2 sodiums here. We have 2 hydrogens, 4 hydrogens. So we need a double of this. Now that gives us 2 oxygens, and by George, we have 2 oxygens. I think that worked. The next one, we have 1 hydrogen, we have 2 hydrogens. Let's double this. 1 lead, 1 lead, 2 chlorines, 2 chlorines. I think we're done. Now remember, when we're dealing with polyatomics, just think of those as a unit, not as 3 oxygens, just as a lump, okay? It's a ball, basketball. We have 1 silver, 1 silver. We have 1 nitrate, 2 nitrates. Got to double this. That gives us 2 silvers. Got to double this. 2 chlorines. Oh, 2 chlorines. 1 magnesium, 1 magnesium. I think we're done. And I got them all right. Let me get rid of my numbers. Okay, of course there are tutorials. This is the balancing chemical equation tutorials. What it does is it gives you an equation. In the real thing, there are little boxes here in front of each element that you can put numbers in. So this is ethene, an organic molecule, reacting with oxygen to give CO2 and water. I would look at this and say, we have 2 carbons, only have 1. Let's try doubling it. We have For hydrogens, we only have 2. Let's double that. And now the oxygens. We have 1, 2, 3, 4, 5, 6. We need a 3. Yep. Any questions? On Blackboard, the things looks the same, except if you have a 1, you have to put the 1 in. Okay? Otherwise, you don't. In real life, you don't. Tutorial, you don't. Blackboard, you do. Look at this guy. This is calcium carbide. Calcium carbide reacts with water to form acetylene. Acetylene's a gas. It's the gas you use in a, quote, acetylene torch, right? And you form calcium hydroxide. We have 2 carbons, 2 carbons. 2 hydrogens, 1, 2, 3, 4 hydrogens. So we have to double up on our water. That's it, by George, that's all we had to do. Now, this is actually a reaction that has history. Back in the old days, miners would go down into coal mines where it was very dark, right? And they didn't have lithium batteries to power little flashlights. So instead, they had this little lantern on their head. And it had calcium carbide, water, and they lit it on fire. And every time they needed to see something, they'd push a button, little calcium carbide would go in, it would get bright, etc. Now, considering that methane gas, which is explosive, accumulates in mines, this wasn't a great idea. Nonetheless, they did it for 100 years. This also is known as the Banksite reaction. Now, when I was a child, believe it or not, you could buy these little cannons called Banksite cannons. You put calcium carbide in here, water in the bottom of the barrel here, and this you push for a spark. So, hit the little button, calcium carbide falls in, you make acetylene gas, you reach in, push the button, oops. Let's try that again, because it's kind of neat. We're all the way back here. Sorry. Sometimes this thing bounces. All right, push the thing, that makes the spark. And you get a real cannon sound. You can put little marbles or something in the barrel here. They fly all the way across the yard. It was just so much fun. You can't buy them anymore, but it's a shame. It was so much fun. What was also fun on Blackboard, there's this, a balancing equation worksheet. This is not for credit, relax, but lots of things to do to practice balancing basic equations. Any questions? All right. Types of chemical reactions. Now, this is kind of like the taxonomy of reactions, and that's biology, which we all despise, of course. But the only good thing about classifying reactions into types is it makes it easier to predict products. We'll see that in just a couple minutes. First ones we're going to look at are synthesis and decomposition. Synthesis reaction is very simple. We take 2 or more things and make a new substance. For instance, carbon plus oxygen, make barbecue, we make CO2. We are taking two compounds, these are both elements, and we make a new compound from them. Synthesis. We can also do synthesis from compounds. This is organic reaction. Again, this is ethene plus HBr to give bromoethane. Two things making something different. Synthesis. Do it backwards and we get decomposition. If we take copper 1 sulfide, heat it up, by George we get copper metal and sulfur. What's one of the early ways to make copper metal? We've done this in lab. No, we haven't. That's the other class. But calcium carbonate. Calcium carbonate is basically limestone, chalk, marble, whatever. But if you heat it up, you get calcium oxide. CO2 is evolved. Calcium oxide is what you call lime. Okay? It's just nondescript gray powder. But if you take this nondescript gray powder, dump it into water, and let it be exposed to air, the reaction goes backwards. And by George, it turns into calcium carbonate. This is cement. You start off with limestone, make lime, add water, CO2 comes in slowly and makes limestone. Haven't you? In lab, we did a decomposition from ammonium hydrogen carbonate. If you recall that, you heated this up, did a whoosh on the top of the tube, and you could smell the ammonia. All right. Replacement reactions. Replacements come in two types, single and double. In a single replacement reaction, element and a compound are going to react, and they're going to form an element and a compound. We simply swap partners. So if we take lead for chloride and react it with fluorine gas, we wind up with lead for fluoride and chlorine gas. We have simply swapped the element into the compound. There's a general rule for these, and that is, if we have a nonmetal, we will replace the nonmetal in the compound. If the element is a metal, it will replace the metal in the compound. Metal replaces a metal, nonmetals replace nonmetals. You recognize one of these things because we have an element and a compound making an element and a compound. Now we've done one of these in lab. Remember, we took a nail that was nowhere near this shiny, submerged it into copper 2 nitrate. Our nail picked up the copper metal, and this is the reaction. Iron replaced copper, and the copper metal replaced the iron and was deposited on the nail. Single replacement reaction. Now we can also do a double replacement reaction. In a double replacement reaction, we're going to take the ions and simply swap them. So the silver will pair with chloride, the sodium will pair with nitrate. We wind up with silver chloride and sodium nitrate. Double replacement reaction. Simply swap. Now, in order for a double replacement to go, we must form a product that's insoluble, so this is a solid, or we must form a gas. Something has to pull the reaction over, otherwise they're just sitting there in solution together and nothing is happening. We'll talk about how we know which things are insoluble in just a minute. The final class we're going to do, oxidation and reduction. Now, way back in chapter 3, we talked about oxidation numbers. We're going to talk a little bit more about it today, but in a redox reaction, that's what they're called, the oxidation numbers change. So, here we have carbon and oxygen making CO2. This is a synthesis reaction too, isn't it? But remember back in chapter 3, we said that the oxidation numbers of elements, by definition, are 0. We also said, back in chapter 3, that oxygen was always going to be a -2. Now, it's not always, to be honest, but it's usually a -2. If this is a -2, we have 4 negatives here, right? To make it neutral, the carbon must be +4. Bottom line, this is an oxidation reduction reaction because oxidation numbers have changed, 0 to +4, 0 to -2. If they've changed, it's redox. All right, that's the 4 groups that we're going to talk about. Fairly simple. Look at these and simply assign them as synthesis, decomp, or replacements. Our first one, we're taking 2 elements. We are making a compound. This is obviously making something new from 2 things. It is a synthesis and actually from the elements. Here we have lead 4 chloride reacting with fluorine to give lead 4 fluoride and chlorine. The nonmetal has replaced the nonmetal. Element in a compound, element in a compound. It's a single replacement. Sodium sulfate reacts with barium chloride. We wind up with solid barium sulfate and sodium chloride in solution, aqueous. The sodium has replaced the chlorine, the barium has replaced the sulfate. This is a double replacement reaction. Look quickly at these. First one here, we're taking 1 compound. We are making two things from it. This is obviously decomposing, isn't it? This is a simple decomposition reaction. Now, this is the one that most people miss. It's always on the exam. Sorry, won't be this time. You look at this and we have an element and a compound, right? Everyone wants to say single replacement, but what are we doing? We're making a new compound, aren't we? That's synthesis. And the last one here, we have an element and a compound. Making an element and a compound, by George, this is single replacement, isn't it? We wind up with oxygen gas from our nonmetal. The chlorine goes with the iron. All right, like I said, the whole point of being able to classify reactions is to allow us a good shot at guessing what the products are, predicting the products. So let's just look at some examples of that. This is a synthesis reaction, and it involves a metal. That's what you look for. Is it a reaction with a metal or not? If it's a reaction with a metal, you are going to make an ionic compound. So when we take aluminum and add it to our bromine, we do a vigorous reaction, and we're going to make an ionic compound. So you enjoy the reaction while it goes. Just don't breathe. Very toxic. And we're making this new substance. Now, this new substance is going to have aluminum and bromine in it. Aluminum forms a +3 ion. Bromine's a -1. We are going to most likely, and this is a best guess, okay? It's always a best guess. Most likely, we're going to make aluminum bromide. Now, this equation isn't balanced. Go ahead and balance it quickly. We have 2 bromines, we have 3 bromines. Let's double that. When we did that, we're both even now, but we have 2 aluminums, only 1. Let's double that. We need 6 bromines here, we have 2, put a 3 in. And we got it. All right, let's look at our next synthesis reaction, and this one is going to involve nonmetals. Very simple reaction. What you do is you look at the valence electrons, see how many bonds they typically form, and then guess as to what the product is. Now, we've seen this before. This balloon contains hydrogen. The room hopefully contains oxygen. When you combine the two, such a neat reaction, we wind up with something. Now, the something that we wind up with, we're going to look at our 2 reactants. Hydrogen, group 1, 1 electron. Oxygen, group 6, it tends to have, well, it has 6 valence electrons and forms 2 bonds. It's kind of a perfect setup. Gonna make a bond here and here, and we get water. Now, once again, this is not balanced. Two oxygens, one oxygen, let's double this. Four hydrogens, two hydrogens, let's double that. That gives us four hydrogens, 1, 2, 1, 2. I think we're good. Next, let's do decomposition. Now, decomposition really is a guessing match because so many things happen at once, you really just have to look for clues. Okay? This is nitrogen triiodide. It's a molecular compound. Very simple to make, actually. You take ammonia and you take iodine, mix them together, ammonia and water, and this black stuff falls out of solution. You take and you filter it off. So this is the filter paper. We have filtered it off and then let it dry. Now, the neat thing about nitrogen triiodide is that it's a contact explosive. Perhaps the most sensitive contact explosive that there is. So once these papers are dry, we're going to set this off using a feather. Simply touching that little guy, and that's what you get. Wow. Good thing TSA doesn't know how simple this stuff is to make. Right? All right, so what in the world is going on here? The clue is this giant plume of purple. What's purple? Iodine. Iodine has a very high vapor pressure, which means it goes directly into the gas quickly. And just sitting here in a little watch glass, you have these streams of purple coming off. So our best guess here is that we are decomposing into elements and that one of them is iodine. If one is iodine, good chances the other is nitrogen. They're both diatomic. Quickly balance it. Three iodines, two iodines, double this guy. That gives us two nitrogens. We have six iodines here, only two here. Stick in our three. And I think we're done. Most simple explosive reactions actually involve the formation of nitrogen gas. That's because energetically it's way downhill. Because remember, nitrogen forms a nitrogen-nitrogen triple bond. So it's a very stable compound. So we start off with something that's unstable, go to something that's stable, lots of energy. All right, single replacements. Again, the rule is metals and metals, non-metals, non-metals. Here we have a compound and an element. The non-metal is going to replace the non-metal. Our best guess here is we're going to get lead for fluoride and chlorine. We're not quite balanced here, are we? We have 4 chlorines, we only have 2. 4 fluorines, and we only have 2. No odd even, but still not quite right. Let's just insert our coefficient to give us 4 fluorines and get 4 chlorines. Now, the rule, like I said, for single replacements is metal, metal, non-metal, non-metal. And that almost always works. There are a few cases, however, where it doesn't. And sadly, those are perhaps the most important single replacements in industry. For example, if we take copper 1 oxide and expose it to hydrogen gas, we get copper metal and water. If you want to make copper metal industrially, this is the reaction you use, right? Simple. But this is a single replacement, element compound, element compound. But the hydrogen is replacing the metal. Hydrogen's a nonmetal, but in this reaction, it acts as if it was a metal. The other reaction here is even more important. This is what they do down in Gary. Okay? You take iron 3 oxide, heat it up with carbon, coal, coke. You wind up with iron metal and carbon dioxide. Element compound, element compound. But the carbon, which is clearly a nonmetal, is replacing the metal. Again, carbon is acting as if it's a metal. So these are the 2 types of exceptions. They almost always involve hydrogen or carbon. But I won't put those on the exam, I promise. Now for a double replacement reaction. Again, we're just going to swap ions, okay? That's all. It's very simple. The cation replaces the cation, anion replaces the anion. The only thing is, something must be insoluble. So here, the barium is going to pair with the sulfate. The potassium will pair with the nitrate. We will get those as our products. Once again, something must be insoluble. In this case, it's barium sulfate. This is called, in general, a precipitation reaction because we're getting a solid out. Here's an example. If we take potassium iodide with lead 2 nitrate, we will get lead 2 iodide, which is insoluble, and potassium nitrate. You see they are both clear, colorless liquids, solutions. They're both in water. If we take and mix these, however, the lead iodide will form. It's a beautiful yellow substance. If you let this sit long enough, it will sink all the way to the bottom as a little yellow plug. Any questions? Well, the only question that I'm sure is really in your mind is, how in the world do I know that something like lead iodide is insoluble or barium sulfate? How do I know that? Because there are rules. Solubility rules. Group 1 compounds or ammonium. If that's your cation, everything is soluble. Group 1 or ammonium, soluble. Simple rule. If it's a nitrate or an acetate for your anion, they're soluble. That's it. Most metal halides, that's with chloride, bromide, or iodide, are going to be soluble. Most. There are, however, exceptions for the heavy metals. Silver, lead, mercury, and copper. Those are insoluble. So most are soluble, these are not. Sulfates, same sort of rule. Most are soluble, except for barium, lead, and calcium. Now, if you have a hydroxide, an oxide, or a sulfide, they're all going to be insoluble unless Rule 1 applies. Rule 1 applies, they're soluble, otherwise, hydroxide, oxide, and sulfide, insoluble. And the same sort of thing for carbonates and phosphates. They're insoluble unless they're Rule 1. Now, I know the last thing you need is another set of rules to remember, but really all you have to do is just remember these couple exceptions, okay? And again, on exam 2, you will get to have a 3x5 card. So if you have trouble, just write down the exceptions. Let's see how this works. Silver nitrate. Well, we remember silver, don't we? Silver was one of the bad actors. But here we paired it with nitrate. The rule says nitrate or acetate are soluble. Magnesium chloride. The rule says except for the heavy metals, metal halides are soluble. Magnesium is not one of the heavy metals, it's soluble. Remember your exceptions: silver, lead, mercury, and copper. Most sulfates are insoluble, aren't they? Except for anything in group 1 and ammonium. Sodium is group 1. It's soluble. Again, a metal halide, but silver. Silver was one of our heavy metals, wasn't it? Silver chloride is a classic insoluble solid. Really, for the exam and for class, you want to remember the classics. Silver chloride is one of them. We remember barium as a bad actor, but again, it's paired with nitrate. Anything with nitrate is soluble. We just saw beautiful yellow lead-2 iodide, right? Well, here it is. It's a metal halide, but lead is a heavy metal. It's insoluble. By now you get the drill. This is a nitrate, isn't it? All nitrates are soluble. Now, almost all sulfates are soluble, except for calcium, barium, and lead. Again, this is a classic. Metal halide, and even though you make cannonballs out of iron, it's not a heavy metal. Therefore, this is clearly soluble. And your last one here, the only thing in your mind is, what in the world is this? CH3COO minus, that's acetate, acetate anion. And just like nitrates, all acetates are soluble. So this isn't so bad, is it? Let's put it to use. Let's write and balance these equations. First thing you need to do, these are double replacements. You need to figure out who is going to be insoluble. Write that, show it as a solid, come up with your other product, and then balance it. Most nitrates are soluble. Most carbonates are not, but this is group 1, so it is. We're going to pair the silver with the carbonate, potassium with the nitrate, and silver carbonate will be our precipitate. Now, balancing, 1 silver, 2 silvers. That gives us 2 nitrates, only have 1 here. 2 potassium, 1 carbonate, 1 carbonate. I think pretty good. Look at the next one. Copper will pair with the carbonate. Virtually all carbonates are insoluble, unless it's group 1. Potassium with the nitrate. Our precipitate will be copper carbonate. Now, let's see. We have 1 copper, 2 nitrates, only 1 nitrate. Let's double it. That gives us 2 potassiums, which is what we have, and 1 carbonate, and that works. See how simple and fun it is to balance equations? It is. It's a game. Aluminum and carbonate will be insoluble. Potassium and nitrate will be soluble. 1 aluminum, 2 aluminum. We need a 2. That gives us 2 times 3, 6 nitrates. We only have 1. We need 6 of those guys. For 6 potassiums, we're going to need 3 of these. So that's 2 aluminums, 3 carbonates, 1, 2, 3, 6 potassium, and 6 nitrate. That works. No.
I'm just writing the last one.
Again, with any luck, this is reporting. So, all right, go ahead and run through these quickly. Again, decide who's insoluble, and then give it a quick balance. Silver will pair with chloride. That will be insoluble. That's a classic. And we will get magnesium nitrate. Magnesium is +2, nitrate is -1. So we're going to need 2 silver nitrates, which will give us 2 silver chlorides. Yep. Another classic here. Barium will pair with sulfate to give barium sulfate, which is very, very insoluble. That will leave us sodium nitrate. Now, barium is +2, sulfate is -2. So that works. We have 2 sodiums and we have 2 nitrates. By George, that works too. We just need a 2 in front of our sodium nitrate. The last one, lead is going to pair with sulfide. Remember, sulfides, oxides, hydroxides, insoluble, especially with something like lead. We have 2 nitrates, we have 2 sodiums. That balances. We simply need 2 sodium nitrates. Yep, that's all we need. Any questions? On the exam, you will be required to do something like this, write in balance, and figure out who's insoluble. All right, our last group here, redox reactions. Again, we said redox reactions are the class of reactions where the oxidation number changes. If the oxidation number increases, it's called an oxidation. If it decreases, it's called a reduction. Now, there's a different way that I've used to remember it. We'll see that in a minute. Oxidation number, going back to chapter 3. You take the elements in their standard state, that's in the periodic table just sitting there. That's a 0 by definition. Next, if your compound contains a metal, the oxidation number is the same as the charge. That's as simple as it could be. If it's a metal, oxidation number, same as charge. Magnesium bromide, +2, -1. In terms of oxidation numbers, +2 and -1. Lithium phosphide, lithium is +1, Phosphorus is -3. Oxidation numbers +1 and -3. So, if it has a metal, you're set. If, however, it's nonmetals or semimetals, so a molecular compound, then you have to look at the full set of rules. Now in chapter 3, we only looked at 2 of the rules. Here's the rest. Elements are 0. Metals are going to be +1 or +2, whatever. It's the charge on the metal. Fluorine is the most electronegative element. It's always going to be a -1. Halides are basically all -1. Compounds with metals. This is where it gets confusing. Is your hydrogen bonded to a metal? If it is, it's a -1. If it's bonded to a nonmetal, it's +1. So for hydrogen, you need to look at what it's bonded to. +1 or -1. Oxygen, we will say, is always -2, even though it's not, but it almost always is. Halogens are -1 unless they're bonded to oxygens, like chlorate. Sulfur, selenium are -2, just like oxygen, unless they're bonded to oxygen. So again, these are sets of rules. You can write them down. You can remember them. They're not complicated. Let's see how this works. We have, what is the name of this? Sulfur trioxide, right? No bottom, and it's molecular. I would look at this and say, okay, the oxygens here are going to be -2. And we have 3 of them. That's 6 negatives, right? This guy has to be neutral. If we have 6 negatives, the sulfur must be 6 positives. That's simple. Let's do another one. HNO3, this is nitric acid. We'll learn that in chapter 8. Looks like this. Here's our hydrogen. It's bonded to one of the oxygens. So the oxygen is going to be a -2. The hydrogen is bonded to an oxygen, so it's +1. We have 6 negatives, 1 positive. The nitrogen must be +5. Neutral compound. Any questions? Now, the questions on the tutorial and on Blackboard are a little more obscure than this sometimes. Okay, let's just look at a couple. This is simple. And there are simple ones on Blackboard, yes there are. You look at this and you say this is lead nitrate, lead 2 nitrate actually. Lead's a metal, isn't it? The oxidation number is the same as the charge. Lead is +2. Here we have pH 3. Phosphorus trihydride. Now, we remember that hydrogen has a rule, doesn't it? If it's bonded to a metal, it's -1. Bonded to a nonmetal, it's +1. Phosphorus is a nonmetal. Therefore, hydrogen is +1. That makes the phosphorus here a -3. Any questions? Now we'll see a couple more obscure ones in a couple minutes. How do we recognize a redox reaction? Well, what you do is simply look at your reaction and to see if the oxidation numbers have changed. There are two things that you have to be able to do. One is recognize that it's changed. That means, yes, it is a redox. And the other is identify which element has been oxidized and which has been reduced. Here's the simple rule. Oxidation is the loss of electrons. You can write that down, by George. Oxidation, loss of electrons. Remember that, and you got it. Okay. Here we have aluminum reacting with iron 3 oxide to give iron metal and aluminum oxide. Question is this a redox reaction? The way to do it is just to go through reactants and products. Aluminum is an element, it'll be 0. Iron will be -2. That's 6 negatives. Each iron must be +3. In the products, iron is an element. It's 0. Oxygen is still -2. This is a metal, so aluminum will be +3. All right, so who has been oxidized and who has been reduced? The oxidation numbers have changed. 0 to +3, +3 to 0. So yes, it is redox. Now, oxidation is the loss of electrons. Which of these elements has lost electrons? We go from 0 to +3. How do we do that? We lose 3 electrons, right? 0 to +3, we lose 3 electrons. Therefore, this has been oxidized. That means that the iron, which gained 3 electrons, has been reduced. Any questions? Now, there is something that chemists do to confuse students. Okay? I won't do this, but you can't ever guarantee what other people will do. The thing that causes this guy to be oxidized is called the oxidizing agent. Iron 3 oxide causes aluminum to be oxidized. It's the oxidizing agent. Likewise, aluminum causes a reduction of iron. It's the reducing agent. So this is just a little bit of obscure nomenclature. I won't use it, but other people will. Okay? All right, let's think about this reaction itself. I promised you we would. This is called the thermite reaction. In this little flower pot here is a mixture of solid aluminum and solid iron 3 oxide, just all mixed up. Now it's a little flower pot. They have a hole in the bottom for water, right? What we're going to do is ignite this. The reaction is going to proceed. When it does, iron will be formed. It will dribble out of the hole in the bottom into this big flower pot filled with sand. It is such a neat reaction to do. It's even fun to watch. But you want to wait. You see the molten iron just pouring out. And when you're done, you never know when it's quite done. When it is quite done, down here in the bottom, there's this little slug of white hot, molten, or now set iron. Isn't that neat? When it cools, it looks like iron, but it's still really hot, actually. Thermite reaction. Again, at USC, I used to do this at the class of 500 people all the time, right in front on the bench. People in the first 3 rows got sparks, but nobody died. But again, you can't do this here, but it's so much fun. It's a shame, though. Sometimes people have a tendency to take something that's very fun and use it in bad ways. This is a bad way. It's called a thermite bomb. What you do is you fly over a city and you drop these little suckers on people's houses. When they hit, you get the thermite reaction. And the houses just go whoosh. This is from World War II. This used to be a neighborhood. Not a good thing. Such a fun reaction, such a bad use. All right, look at these. Determine if they are redox or not, and determine who was oxidized and who was reduced. We start off with tantalum and bromine. They're both elements. They're both 0. We wind up with a compound. It's a synthesis reaction, isn't it? The halogen is going to be -1. There are 5 of them, so that means the tantalum must be +5. So, first of all, this is a redox reaction. We've gone from 0 to +5, 0 to -1. Yes, it is redox. Step 2, who has lost electrons? Tantalum has gone from 0 to +5. To do that, you must lose 5 electrons, right? Tantalum has been oxidized, bromine reduced. Do the next one. Element in a compound, element in a compound. Single replacement. The elements are going to be 0. The oxygen will be -2. Aluminum's a metal, so it's a +3. We have 2 minuses here. That's at -4, making the silicon a +4. Yep. All right, who has been oxidized? Who has lost electrons? We're doing +3 to 0. That's gaining 3 electrons, right? And 0 to +4, that's losing 4 electrons. Silicon has been oxidized, aluminum reduced. Quickly do the first one. Sulfur is an oxygen wannabe, right? So it's going to be a -2. Sodium's a metal, it's +1. Lead's a metal, is +2. So our oxidation numbers. Because the oxygen is -2, and there are 3 of them, the nitrogen must be a +5. You don't have to break down nitrate. But if you look here, sodium, sodium, lead, lead, sulfur, sulfur, nitrate, nitrate. This is a double replacement reaction. And unlike single replacements, you never have redox in a double replacement. Never. Last one. Oops. That wasn't supposed to show yet. Hydrogen's an element. Nickel's an element. Element in a compound, element in a compound. Single replacement, right? We're going to go from 0. We're bonded to a nonmetal, so that's a +1. 0 to +1. The chlorine stays the same. The nickel goes from +2 to 0. Hydrogen going from 0 to +1 has lost 1 electron. That means it has been oxidized. Any questions, guys? Oxidation, loss of electrons. All right, there's a tutorial that can be really confusing. What is this? It's antimony. Antimony is a transition metal, so this is antimony 3 oxide. We're going to make antimony out of it. We're reacting it with this polyatomic ion, vanadium oxide. The whole ion here is a +2 charge. Question is, what's happened to the vanadium? Was it oxidized or reduced? Here we're going from VO +2 to VO2 plus. So let's take this apart. The oxygen here is going to be a -2, isn't it? We wind up with a net +2 charge. So if the oxygen is a -2, the vanadium must be a +4. These are what's called half reactions. They're not balanced. Typically, in general chemistry, you will use a lot of these. You're just showing what's reacting, as opposed to balanced. So, look at our vanadium here. Oxygen is -2, vanadium must be +4. -2, +2, and we wind up with a net 2+. On this side, oxygen is still going to be -2. There are 2 of them. We still have a net positive charge. So this is 4 negatives. The vanadium must be what? +5. So, what has happened to the vanadium? It has gone from +4 to +5. Does that mean it gained an electron or lost one? It lost one. It has been oxidized. Now, they're not all quite this complicated. Here's one that's very simple. Thallium, +4 goes to thallium. Again, a half reaction. In order to go from +4 to 0, what do we have to do? Gain 4 electrons. This is +4 metal. This is an element, it's a 0. Gain 4 electrons to make it 0. It's a reduction. I believe the blackboard is basically like this. You choose either or. But I think you have to write the word, as I recall. Yeah, you might. And please be careful how you spell oxidation and reduction. People miss it all the time just because of spelling, or because they put a space before it or a space after it. Don't do that. Just the word. All right. In the lab that wasn't, we had an activity series shown. Now, we had no clue what this was. Basically, it had to do with oxidation potential, but this is reactivity of metals as you go from top to bottom. These are very reactive, react with water. These guys will react with acids. These are highly unreactive. Hydrogen fits right here, separating the reacts with from unreactive. So, when we look at a reaction, and again, this is a half reaction, we have sodium reacting with acid to give us sodium ion and hydrogen gas. What you want to do is find each of these guys on the activity series. Hydrogen is here, sodium is way up there. The higher up it is, the more reactive it is, and the more vigorous the reaction will be. So, the metal and the ion, if the metal is higher than the ion, a reaction will occur. The further it is away, the more reactive it is. If the element is more reactive than the ion, the reaction will occur. Something to remember. We did this in lab. This one worked. We are taking silver as the ion and copper as the metal. We look at the activity series. They're both down here. But copper, which is the metal, the element, is higher than silver, the ion. So this reaction will go as written. Copper is more reactive. It will replace the ion in solution. Now this is the reaction we did in lab, sort of. We have silver nitrate solution, and to this we're adding a chunk of copper wire. We sit back and we watch it for a minute or two. After a couple minutes, we start seeing fuzz form on the copper. That fuzz is silver metal. We are starting with copper in silver in solution. We wind up with silver as a solid. After 20 minutes or so, we wind up with a really fuzzy piece of copper wire. Again, our reaction, single replacement, silver nitrate forming copper nitrate, copper metal, copper ion, silver ion to elemental silver. Why is it blue? Remember we did the blue copper sulfate, right? Copper salts are generally blue in solution. Look at this one. Our metal and our ion. We find iron. We find copper. Remember we did this in lab again. Put the iron metal in the copper solution. Got iron in solution and copper metal deposited. Finally, let's look at these two. I want you to tell me which of these reactions will occur. We have aluminum and lead. The element and the ion. The element is more reactive than the ion. This reaction will go, this one will not. Now, in general chemistry, you will revisit this and you'll talk about it in terms of oxidation potential. That's a voltage that's associated with the way they order themselves. But right now, we're just doing it in a simple descriptive way. Remember, element is more active, the reaction occurs. All right, questions? Aluminum and chlorine react to form a compound, which is true regarding the reaction. Compound will most likely be ionic. Well, aluminum is a metal. Of course it'll be ionic. Here's our reaction. Aluminum plus the nonmetal aluminum chloride. Oxidation number of aluminum in the reactants is 0. It's an element, of course it's 0. Molecular formula will most likely be AlCO3. Well, yes, it is. Aluminum plus 3, chlorine minus 1. So it's an all of the above. All right, which of these are going to be insoluble? Now, let me be rigorous here. Nothing is insoluble. Everything is soluble to some extent. Again, in general chemistry, you'll be introduced to the solubility coefficient, which is an equilibrium constant. And it describes just how soluble something is. When we say insoluble, that means we're going to see a precipitate. All right. Barium sulfate. Well, that's one of our classics, isn't it? Lead to iodide. We saw that. Beautiful yellow stuff. Copper nitrate. Wait a minute. We remember nitrates. They're all soluble. So, A and B are insoluble. C is not. All right. In the reaction, what happens to fluorine? First of all, what kind of reaction is it? It's a synthesis, right? Lead is an element. Starts off at 0, right? Fluorine is an element. Starts off at 0. Here, lead is +4. Fluorine is -1. Our fluorine has gone from 0 to -1. That means it's gained an electron. Is that oxidation or reduction? Reduction. Gained electron, reduction. So which of these is right? Changes from 0 to -4? Nope. 0 to -1. Does not change. That's not right. -1 in the reactants? Nope. It's 0 in the reactants. It's a dreaded none of the above. Now on exam number 2, you typically have a problem something like this, where you're asked for the oxidation numbers. So look at this quickly. We have a rule for oxygen, don't we? Oxygen is going to be a -2. That gives us 5 times 2, 10 negatives, right? So each nitrogen must be a +5. Let's do one that's a little more interesting. This is chloric acid. Basically, it's chlorate with a hydrogen attached. Now, compound looks like this. Hydrogen is attached to the oxygen. So, Every oxygen is gonna be a -2, isn't it? The hydrogen attached to the oxygen, +1. So this is 6 negatives, 1 positive. The chlorine is +5. All right, well, thus endeth the chapter. Today we did 3 tutorials. These are 5 points each. I hope everybody has, quote, learned that the tutorials can be extremely important to your grade, right? They can. But now I'm going to up the ante just a little. Is everyone sitting down? Yes. If you take exam number 2 and your total points on Blackboard are 350 or above, and that includes all of the extra credits, 350 or above, I will give you an A in the class, and you will not be required to take the final. Let me say that again. If your total after you take exam 2 is 350 or above, A in the class, no final exam. Oh my goodness again. Do the tutorials, do everything you can to scrape and get the extra points to hit 350. Please. All right. Have a good day.
Hi, Dr. Young.
Yes.
So I didn't give this to you, and I think this was part of Chapter 5 labs, right?
Right.
Okay, so can I hand them to you now?
Sure.
Thank you.
Not supposed to do it, but I will.
Thank you so much.